understand that what is an experiment? It's an experiment, okay? For example, tossing a coin or rolling a die. An experiment has a set of outcomes.
Yeah.
Experiment has set of outcomes. That is lovingly named as sample space, which is equivalent to this sample space. Now, what we need to know, let's say now, example, we are rolling a die. And we have the set of outcomes. What? We have the set of outcomes as 1, 2, 3, 4, 5, 6. Okay. Now we are interested in the event that it gives prime numbers 2,
Okay.
3, and 5.
Yeah.
So the event is a subspace of sample space,
Yeah.
a set of outcomes corresponding to the scenario. Now we want to understand that what is the probability of this event, the chance of this event.
Okay.
What is the chance of this event? That is what we are trying to understand.
Yeah.
There are various methods to it. Okay, and I will tell you how
Hmm.
people started thinking about it. They started thinking that, okay, this is our set of outcomes 1, 2, 3, 4, 5, 6. And out of this, I am choosing 2, 5, and 3. So it
Yeah.
seems like it's what is the chance of getting this? It's like 3 by 6 almost, right?
Yeah.
3 by 6, it makes sense, right? So what we are looking for? We
Yeah.
are looking for this number of elements in the event.
Yeah.
In event by number of elements in sample space. This is total sample space and this is set of subset. This is the event. This is makes the event.
Yeah.
The green part is this. You understood? So it turns out to be 3 by 6.
Yeah.
So therefore it turns out that counting the number of elements, so now to count this number of elements, we need combinatorics. If it's a complicated set, you need to count the for combinatorics. We will understand how combinatorics is required. Okay, this for counting these elements, we need combinatorics, and for this too. This is where the combinatorics knowledge that you have gained till now, it will help you to count the number of elements in this set, all the properties.
Okay.
This is 3 by 6. This is the basic idea. It's half.
Okay.
But there is a problem in here. There is a con in this approach. What is a con in this approach? There's a very significant. There's a very like significant problem in here.
Okay.
The issue is, the main issue is, what if the die gives more 5, 6 than 1, 2, 3, 4. That is, what if that case? So let's again draw the diagram over here. So this is the basic idea. We have got this 6 ones. 1, 2, 3, 4. I'm writing 5, 6 in a different color to make sure that 5, 6 are given a much more stress. Like, let me write in different color. 5, 6 occurs much more often, that is, than this. Then understand, let's try to draw. We are trying to look for 2, 3, and 5, right?
Yeah.
Now
Which
tell
means
me,
5 has more weight attached to it than 2 and 3.
yeah. That means understand this very carefully. In the previous framework, if I would have told the event was instead 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6.
Everything had equal weights.
Yeah. So in the event, if I told that in the previous, let's say the event is here this, and here
Yeah.
the event is this. So here the
Yeah.
event is 1, 2, 3, and 4, 5. Here the event is 2, 3, and 4.
Yeah.
Now understand this. Tell me one thing. Which one has more chance? Which one has more chance? Which event has more chance of occurring?
For example, in the in the first box, event 2 and 3 have the same chance, but event 5 has more chance because it has more weight attached to it.
Yeah.
And in the second example, everything have equal weight, so everything have equal chance.
Okay, here also 5 makes sense like this. Here also same thing. I'm so sorry. Yes, same framework. But
Okay.
now which has more chance of occurring? We have chosen the
I
same
think
framework. 1, right? Why? Why? Why 1 has more chance of occurring?
1 has more chance of occurring.
I mean this case. You told this case has more chance of occurring, right? More chance, right?
No. I told you 5 has more chance of occurring.
No. This case, I told this event. Which event has more chance of occurring?
Yeah, in 2, 3, 5, the event 5 has more. Okay.
Together, like in a together format.
Okay. Then in that case,
Tell me, it's simple.
the event 1 has more chance of occurring.
Why? Because why? So
Because you have 5 occurs more times than.
Lovely.
Yeah.
Now understand that in computing in the same manner as before, computing as the same manner as before,
Okay.
here the number of elements in event by number of elements in sigma is still half 3 by 6, and in this case also it's 3 by 6. Let's select this. Just give me a minute. Can I select this? I think yes. Just give me a minute. I'm trying to walk with this if it's possible. Duplicate. Can I not change this? Can I not replace this? Okay, anyways, let's continue with the basic. So understand here, I talk of the same thing over here now. That's number of elements.
Yeah.
In event. Here also number of elements in the event. by number of elements in sigma is 3 by 6. So it's
Yeah.
half. Both are half.
Yeah.
But we can
Yeah.
understand from intuition that one must have greater than 2. It's intuitive.
True.
So this idea cannot be modeled by this definition. So this
True.
scenario.
Yeah, Sujit. Yeah, Sujit, only 1 second. The answer that I told, since 5 has more weightage, so even one occurring a lot is sensible, right?
Yeah, of course. It makes sense, right? It's
Okay.
intuitive.
Yeah.
So the idea is that this definition of probability, this
Does not hold. Yeah.
definition of probability sucks in this case. So what will we do? So we need another definition. We need some other definition. This is called the classical probability approach. So we need something else, and this is where the mathematicians and statisticians and probabilists stumbled upon for centuries. So they sort of did something like this. They told, okay, I cannot do like this. Let's do it in an inductive manner. Let's try to understand the probability. By repeating the experiments, by doing the experiments in hand.
Okay.
In hand. So what is the basic idea? They told that okay, let's understand this. That they told this following, that if we cannot define like this, let's define like this. Let's suppose in this case, let's toss the events. So if you toss these events, that, okay, let's say 5 has more chance of occurring, then this event will, so we toss the events and we get 1, 5, 6, 4, 5, 2, 3, 4, 6, 5, 5, 1, ऐसा आएगा कुछ. So they told that every single step, here the chance of occurrence of the events is 0, right? 2, 3, 4 नहीं आया है.
Yeah.
2, 3, 5 नहीं आया है. ठीक है.
Okay.
So let's try to understand this. 2, 3, 4, let's compute it for this event. And let's compute 2, 3, 5. This is not a random event, I just generated it to make you understand.
Okay.
So 2, 3, 4, 0, 2, 3, 5, 0. Here, I'm just, so what is the idea? That they will compute the number of times it has occurred, the total number of tosses. So this is the definition. They told by this. That's a natural way of defining, right? They told that we'll update the.
Yeah, why have you put 0 for 1? Because 1 has occurred twice, right?
No, because 2, 3, 4 कुछ भी नहीं occur किया, so it's a count 0. So it's like 0 by 1 over here. So one toss, so it's like number of times it occurs, number of times favorable.
Okay.
By total number of tosses, total number of trials.
Okay.
Here 5 has occurred, so it's 0, but 2, 3 hai, 4 hai. Here it's 1 by 1, right? 1 by 2, sorry. 2 tosses and
yes, 0 क्यों वहाँ पे है यार? Why did you put 0 there in the first case?
Because 2, 3, 4 नहीं occur किया ना. It's like number of times this has happening. Any one of them must occur to be in the set, right?
Okay.
When we say an event is favorable, when one of the elements in the event occurs in the experiment, right?
Okay. Yeah, second, first, third also 0.
0 by 3, here also it's 1 by 3.
This is 0 by 3.
No, 1 by 3. It's like we are counting total number of cumulative. We are counting cumulative format. You understand?
No, 1 by 3 I did not understand. Cumulative format in the sense?
So we are counting till number of tosses. It's like this. Suppose you know that the chance of heads is half and chance of tails is half. So you expect that
Yeah.
in 100 number of tosses, it will be almost 50-50, right? Almost.
Yeah.
So similarly here, in large number of tosses, the probability will be actually close towards the actual probability.
Okay.
That is what we are trying. So in 3 tosses, we have got 0 out of 3, and here we have 1 out of 3.
Yeah, that is what I'm asking. How does 1 had come?
1, because till this point of time, 1, 3, 4, 1, 3, 5, 6, till this point of time, only one time it has been in this set. We are counting the number of times it's favorable happening. You understanding?
No, yeah, no. This is where I'm just got stuck because I understand that the first trial we have got 1, so it is 0. Similarly, 0. The second time when we tossed, we got a 5. So for the first it is 0. For the second it is 1 because we have 5 in that set.
Yeah.
In the third time when we tossed, we have got a 6. Since 6 is not available in the first set, we have put 0. Similarly, 6 is also not available in the second set, then obviously it should be 0, right?
0.
Why does it?
But this 1 is carrying away now. Carrying. It's like we have already counted. That is like a tally mark. You know, number of tallies have happened. We are tallying how many times this set has been favorable till this point of time. This set has
Okay, so you are saying that since 5 had occurred once and it was in this set, so basically in the next time also, though we have got a 6 which is not in the set, but in spite of that we are carrying it.
Yeah, it makes sense. Like if you have tossed, you will just not see that toss. You will see all the tosses before, right? To make an understanding.
Okay.
So it's like you're tossing 50 times. Okay.
Okay.
So you will not tell at the 50th toss that suppose it tells the probability is 0, or like the expected idea that expected like portion, or what should I say?
It is not the 50th toss, but it is 350 toss.
Exactly. It's still this point of experiment.
Oh. Okay.
Here it say 4 is coming, so here it's 1 by 4. Here 4 is coming, so it's again 1 by 4. Here 5 is coming, so it's
0. I'm sorry. 1 by 5.
1 by 5. Here
it is 2 by 5.
2 by 5. So here it's 2 again, so it's 2 by 6, 2 by 7.
Yeah.
Sorry, 2 by 6. I'm so sorry.
Yeah.
And here it's 3 by 6. 3 here यहाँ पर, so it's again 3 by 7. Here it's 4 by 7.
Yeah.
4 है यहाँ पर, so it's 4 by 8, and it's 4 by 8 again.
Wait.
It's 6 है यहाँ पर, so it's 4 by 9. Here it's 4 by 9.
5
है यहाँ पर, so it's 4 by 10. It's 5 by 10.
5 by 10. 5 is it is again 4 by 11.
4 by 11, 4 by 12. It's 5 by 6 by 11, 6 by 12.
6 by 11.
6 by 12.
6 by 17. 12.
Yeah. So understand that what it turns out. It turns out that this probability is almost, I mean, it will be continuing for long, and this is not a random toss, okay? It's not a random stuff. So it's turning out that in this long run, it is turning out to be 1/3 and it is turning out to be half. It's like long run. I'm just assuming, okay? So this has much more probability than this. So this makes sense, and this like simulates the scenario.
Okay.
So this is called the frequentist approach.
Okay.
Now there are some issues with it. You can tell, wow, it's so good. It's so good. It's so good. But it's not good. There are some points in here which I want to make. Not so good.
Okay.
Why? So what is the definition? The definition is that number of favorable events by total number of trials.
Yeah.
Okay. Iska limit n tends to infinity.
Yeah.
And number of trials goes to infinity. This is the probability we are looking for. Favorable probability.
Yeah.
Understand, the con is that if this is a definition, we cannot never find the probability, because for every single probability you have to find out and do the experiment.
Yeah.
So it is not possible every
True.
single time for a long time. So it's
Yeah.
understand so much money is required. It's like waste of money.
Yeah.
So people
Yeah.
understood that no, this is not a, like, it's like telling that finding out the probability that a gambler will win is the only way to tell that is to playing the same
Make
game
him-
over and over again 100
Don't-
times and
again,
understand
yeah.
it. Yeah, that doesn't make sense.
Yeah. Yeah.
That
Sense,
doesn't at all
yeah.
make sense. So
Yeah.
how to? So this is not a good idea, but this gave an important idea in the later half of the probability development and statistics development. It's called law of large numbers,
Okay.
which tells that in fact it actually, as n tends to infinity, it actually gives the actual probability. Okay, it actually gives
Okay.
mathematically,
Okay.
but this is not a good logical and approach and mathematical approach to towards a problem. It's like an experimental approach. Okay, it's not a mathematical
understand.
approach. So this is a law of large number, which is the mathematical form of it, and it tells that yeah, what is the idea? The idea proposed here is actually true, but it is not physically, not practically
Feasible.
really bad. Yeah, practically feasible. Practically really sucks. So this is the idea of frequentists. So this was the two ideas prevalent in the initial part of probability development that was trying to understand the classical probability approach and this approach. And we were trying to understand
Yeah.
that okay, this is the case. That but what is the problem over here? We cannot do that. So people are really in a very big dilemma how to do that. And then Kolmogorov came, and then the not Kolmogorov only, but previously like the basic part came, and then the real probability approach via probability space idea.
Okay.
Space idea came up, which we'll discuss in the next class. So that's a
Okay. Okay.
because I have my already students have started entering the class.
No.